Okay.
It's recording on
Just go
from
go
you.
and do first.
Okay.
Yes.
Okay. Oh, should I stop? Just going into,
It's like-
I'm just going to presentation.
Presentation. So do you want a mic for a?
This is on the screen. What did you want something from Zoom? From Zoom?
I believe you're sharing a presenter.
On this screen, you're just seeing one. There's my Zoom window. That's a very good question. That's a very good question. There we go. It's right there. No, no. So if you, where is that bar gone?
Go through windows. Double tap maybe. What is that?
Yeah, we started recording. It's not it. Should I stop this and come back? Let me stop this. I think that might be easiest. So let's stop the screen share and come back. Thanks. Thank you.
There you go.
May I click it?
So what did you want from that? What should we do? Hello? Hello? Hello?
Ready? Hello. Quickly, yeah, I hope everybody's here.
So losses there.
Sure. Thank you all. And then going to principal for CG. And we've been working with them. And then we work is the concept as a result we want to pick for the student that conclude where it is now and first not an invention, but in parallel over the last 50 years, we've been running amazing programs for doing research from the students that are for the world, which is now involved amazing across the globe. It's really spread, not just in the community stuff, equations and such with research being with some. But right now, we can to hear about result of the study in guess. A lot of people ask that, I mean, the cosmology called in our guess, and the first people started that.
Sorry. Thank you so much. We are still figuring out some.
Let's use this mic.
I'll use this mic, the screen sharing thing. Something is.
This one works.
It's okay.
For the YouTube. So something is not found yet.
Okay.
Screen share.
That's good. That's good. All right. Stop. Okay. This is okay. Go to full screen here.
Just take 1 second.
Still thinking.
Yeah.
Sharing presenter mode. All right.
See, no, some moving. How many people are out there? Let's move on.
I just want to start presentation. Thank you. Should I get started?
Yes.
Can you hear me in the back? Or, so, Philip tells that in 2018, we started something here in this room that was called Python and Research. And I am really happy to physically be in this room between 2018. We did all through Zoom. And I've never been in this space before.
It wasn't Zoom in 20, was it?
It was Skype.
Live.
It was Zoom. It was Zoom. Okay. Yeah. Okay.
Invented it. Very well. Pioneers.
So if you put lights on in the front, that will help fall asleep. Be good for everyone.
So these lights.
I'm the lights. Just because the night skies are many of my slides are.
No, these lights are
Lights.
yeah.
Okay, this is great. You can see much more. No. Okay, so I'm going to talk about galaxies inside and out. I'm going to talk about the populations of stars in 3 galaxies: in our own Milky Way galaxy, the Inner Galaxy, and the Triangle Galaxy. And what I'll do is throw out a list of this that ultimately will hopefully be just teasers to get conversations going. Post after my talk conversation about any of these topics here. So this is the Inmate Galaxy that you see in the picture. This is Santa Cruz and I have worked together on. This picture was taken by Robert Endler, an astrophotographer who works as a doctor by day, astrophotographer by night. What I'll talk about was put together with Keck telescope. So I want to show you a picture of Keck telescope. Coming into interview graduates, Laurie Hatch photo of Mauna Kea sunset, and those are the 2 Keck 2 10-meter telescopes, segment telescopes. So quick outline. We're going to talk about the build-up of the QA. So this is how, and I'm a travel fan. We'll also talk about 2 surveys, Hello Survey and NGBS, Next Generation Birth Survey. I'm going to talk into the 32 plus minus 1. So M31, M32, and 33. And those are through, again, acronyms. There's another acronym actually called TREX. Triangular Extended Sentence. And we first did a of the triangular galaxy, a map of the stars and cross it look like a dinosaur. So with the TREX. And then I'll say a little bit about new groups of galaxies, and that's through a survey called PICE. Okay. Again, I'll cover a lot of different things, and I apologize for covering them not great detail, but please ask questions. Okay, so the Milky Way, and oops, let's skip this slide. Sorry. I want to go to the accretion tree of the Milky Way stellar halo. And this is a survey called Halo 70. So I'm literally using acronym, at least the expanded version of this. This is looking at halo assembly in the CDM, that's what the L stands for. So it's observations in 7 dimensions. 7 dimensions, 3 positions, X, Y, and Z. Key components of velocity. V sub X, V sub Y, V sub Z. And the 7th dimension is measuring the chemical composition of these stars. So it's 3D kinematics, represent big stellar populations, and along 5 pencil beams to the galaxies. So this is something that was as a combination of Hubble archival imaging data. So if you have multiple images visible, you can see stars creep across background wallpaper of distant galaxies. So there's a wallpaper of distant galaxies that covers every sky. And if you take images with high resolution, angular resolution, far enough apart in time, then you can see stars in position by a very small amount of precision in the measurement of the position of individual stars, something like thousands of pixels. So it's a very subtle amount of motion. I like to think that these sort of surveys are when the time allocation committee rejects your proposal and says try again next year, it's going to be a stronger proposal next year with your time baseline and thrown the stars a little bit further apart. So one of the impetus of these sorts of surveys. We're measuring what's called the proper motion of stars in the X and Y plane. This is important we measure through dropshift, of course. Multi-epoch Hubble's telescope imaging. Now we're using Hubble's telescope as Gaia, and we'll be using James Webb and the Roman telescope as well. Now this wallpaper on Galaxies is something to study for my research once upon a time. Now I've relegated to background wallpaper. We also get spectra of these galaxies because in the same piece of aluminum where we've got some slits to get spectra stars, there are also slits that are cut on in galaxies. We have up to 32-hour exposures with the telescope of these galaxies. And this has spawned a whole bunch of papers from the Halo 70 survey, the so-called candles fields, and also the foreground of the Andromeda galaxy. The radial velocity for about 200 stars, but have spectra about 1,500 galaxies. This is the Keck part of the program, and chemical abundance with our PhD student, Kevin McKinnon. The underlined folks are all people who are either graduate students or postdocs who've been working on the A11D survey. Miranda Atwell and Cunningham, Alice Thiessen is now a faculty member. She was a postdoc when she started this. Kevin McKinnon is a PhD student. And the folks in the second row are who've been working with us in Galaxies. She's part of Vidmo Barrow, Charlie Monroy, Santa Cruz, Yicheng Guo, Yes. Okay. Emily's PhD thesis was based on this. This is what Emily did back then, and as Thiessen was a postdoc when this work was done. Of this, I'll be showing you a picture of people who did the work. I'm only here to talk about it. And this is an example of some work in the Halo 70 survey. The bottom line from this is if you look through the galaxy in different directions, you see things. Just because the galaxy is not well made, it's the galaxy is through cannibalism, and it hasn't digested of its bits yet. You see the undigested or partially digested remains of the galaxies that the Milky Way cannibalized. You can see this color coding in each field. Every field is a different. Every color is a different pencil beam through the sky, and what you're seeing is motion, average velocity in the phi direction, the dispersed velocities and these in the radial direction, the mix of distances, line of sight distance, the dispersion in the phi direction, tangential direction. Theta is the polar coordinate. We're working in spherical polar coordinates. And then what you see here is the so-called astrophysics parameter. Are stars moving in tangential orbits or radial orbits? And if you can see again variation across the polar side. This is from Emily Cunningham's papers from her PhD. And the idea is to put the context of the accretion history of the Milky Way. If the Milky Way accreted, most of the cannibalism was done a long time ago, and it only ate snacks as opposed to have each. And then this would have been erased by now. All of this, it's very easier to digest. And if you give yourself lots of time, you digest them. You completely digest them. So clearly, had some large meals, and it ate them relatively. And that's that's the bottom line thinking you can learn from this. But I'm seeing a lot of details when I say this.
Colors are different types.
Different things, yeah. Famous fields for discrepancy reasons. So that's why we chose them, because we want this galaxy will be the 4 weak fields. EGS is at the extent strip goods, solid goods, not, and the cosmic field. So the numbers of stars in each of the fields, the N, the number of Milky Way stars in each of those fields, but we have 1,000 galaxies in these fields as well. We recently, Kevin McKinn recently published this paper, so sorry I haven't updated this yet, on the chemical composition of the stars, the seventh dimension of uncertainty. And again, it focuses on field-to-field variation in the chemical composition of the stars, because it's very well-known relationship between how massive the satellite is that Milky Way 8 and its degree of chemical enrichment. There's a mass-massivity relation in galaxies. The more massive a galaxy, the more massive a galaxy, the more chemically enriched it can be. And the reason for this is very simple. The reason for this is remarkably simple. The explosion energy of stars, type 2 supernovae, the energy of massive stars, I should say. There's a certain energy state here, certain amount of momentum generated by that explosion star. That's the same, no matter what galaxy this explosion takes place in. What does change from galaxy to galaxy, depending on its mass, is the depth of the gravitational potential. Full-mass galaxies have a relatively shallow gravitational potential. High-mass galaxies, say that are 100 times more massive than Milky Way, have a very deep gravitational potential. Milky Way is on the massive side of things. But when you have a deep gravitational potential, an explosive star doesn't succeed in throwing its material clear out of the galaxy. The stuff rains in, and the efficiency with which end products of massive stars get incorporated into the next generations of stars is higher the massive the galaxy, and conversely lower and lower, less massive the galaxy, because more and more of that ejected material clearly escapes the galaxy, and the next generation of stars will benefit from the stellar ancestors. The metallicity is sort of important proxy for the mass of the galaxy that the Milky Way. Remember, these are partially digested remains. They're very hard to sort of diagnose. They were forensically a little bit about reconstruction of events in just a bit. This is some work from Miranda Apfel's thesis. The previous work was from Kevin McKinnon's thesis. But what you see over here are the lines of sight projected into computer models, galaxies that are undergoing embolism. And on the far left is a very strange kind of diagram where the size of the dot tells you the size of the meal. And the vertical axis is when the meal took place. So if the dot is up, the meal took a long time ago. If the dot is very small, it's a small meal. You can see that the galaxy, the middle galaxy at the top, is one that had a heavy meal relatively late, whereas the galaxy at the bottom is better mixed. And you'll generally see that you sort of see this in the variation. In fact, I take this back. If you look at the, let me see if I can point. If you look at over here, the contrast, this galaxy, it had no recent meals. It ate large meal a long time ago. Has had very few cannibalism events down here recent times. This is the time since the accretion, right? So it could have accreted things 30 million years ago, but in the last half of Earth time, this galaxy has had hardly anything to eat. This galaxy, by contrast, eaten quite a bit. So you see there's more variation along different lines of sight in this latter galaxy compared to our galaxy. These are much closer together. Sorry. Now this clicker is working. Sorry. Sorry about that. Okay, so you see these cumulative histograms of velocity are much scattered across a different right in the galaxy that has a recent kind of cannibalism to the one at the top. This is completely simulated from Bullock Johnson 2005. This is something, but what isn't simulated are the lines of sight of how many stars are drawn from. So the point is, this can learn something about the history of our galaxy from the Halo 7 survey. So it's tied to the survey, simulates that survey through a set of simulated galaxies. So this is Miranda. She's a PhD student at UCSC. Okay, I'm going to skip this slide and go on to talking about the inner regions of the galaxy. What I'm talking about earlier is the inner 25 parsecs of the Milky Way. By contrast, our solar system is 8 kiloparsecs from the center galaxy. So it's going up about a factor of 3 in radius from the center of our galaxy compared to our distance from the center. So in a 25 parsecs to the last distance. Now I'm going to talk further out in the Milky Way halo. An outer halo of the Milky Way contains very stars. But the reason it's important is the following. When you get further and further out of the galaxy, galaxies have this very strange property. They contain the dark matter, that part, but we know. They have what's called flat rotation curves. In other words, the orbital speeds of objects around a galaxy don't change with risk. By and large, the orbital speeds of material around a galaxy with radius. Now, if you have a spinning frisbee, the orbital radius is proportional. So orbital speed is proportional to radius. That's solid body rotation. The further out you go from the center to the speed. If you go to something like the solar system, the orbital speed of planets drops precipitously from Mercury, Venus to Earth, and so on. But in galaxies, the speed stays about the same because there's two competing effects. As you get further and further out, you're getting from the center of rotation attraction, but you're including more dark matter. That's interior fuel that's pulling on you. Those effects almost exactly cancel out when it comes to velocities. So that means that the further out you go, the longer it takes for a satellite to go around once. Because, of course, by our positioning, if it's on a circular orbit. But in general, whatever your orbital shape, the further out you go, the longer it takes for a satellite galaxy to go around the Milky Way. And in general, one can see that it takes a couple of orbits of that little galaxy before it gets completely cannibalized. It takes a few orbits. So the further out you go, the longer time scale cannibalism events, the longer that time scale. And that's good news for astronomers because we are, of course, looking for a snapshot galaxy live. So if we can go to the outskirts of a galaxy where the distance of cannibalism memory is the longest, then we can really probe furthest into its past. So the outer regions of galaxies are important for this reason. So I'm going to say a little bit of the search for very distant stars in the Milky Way halo, a kind of stars called RLRI. So this comes from the next generation Virgo cluster 7, NGVS, NGVCS was too hard to pronounce, so NS. It uses the kind of white telescope and a white imager, 1 degree image. And it got 104 degrees, 104 different pointings in 4 filters, ultraviolet, green, and 2 flavors of infrared. It has a certain time domain aspect to it. Even in a given filter, images were taken at least hours apart. Multiple images in each filter were taken at least hours apart. And across different filters, they were observed years apart. So what that means is if something's changing at the brightness of the star, we can easily find them because foreground stars in the foreground of the Virgo cluster, the Virgo cluster is about 16.5 megaparsecs away, 50 million light years away. In the foreground of the Virgo cluster, from galaxies, outer halo, we can find our event. So this led to the robust discovery, most robust discovery, I'd say, compared to other surveys of stars in the outer halo of the Milky Way. 300 parsecs away, 300 kiloparsecs, a million years away. Just by contrast, we are 8 kiloparsecs from the center of the Milky Way, our solar system is. We found things that are 300 kiloparsecs. And this is about 40% of the distance to our nearest big galaxy. So galaxies don't have to be island universes like Emmanuel said they would be in 1750 something. Born in 1724 and died in 1804, somewhere in there. He about island universes, or what we call galaxies. So there's much ocean between these. If you really follow islands all the way out to the periphery, not one between them. the paper that you think a PhD student is working on. And these are examples of what RLRA look like. They are the EEGs of the universe, electrocardiograms of the universe. They have a small and a steep rise. And again, physics of this is well understood. That has to do with the opacity of the star going up, and therefore reacting to the momentum of the photons that are trying to escape that star. So the star blows during that time, almost a factor of 2. Its temperature goes, and then as that happens, the opacity drops. If it becomes more transparent, and other photons escape more easily, and gravity will start to make the star smaller until that repeats. That's periodic. These are phase-like curves. And the typical period of RLRA is less than a day. Anywhere from 6 hours to 18 hours is how. So there are many RLRA known, but we've found some of the most advanced. And again, I'm going to go into the details of what I'm doing here, but this is a small pizza slice of the universe where the most distant stars we found are a little more than 300 kiloparsecs. It's the 6 most distant stars highlighted, but even 100 kiloparsecs, very little is known about a galaxy at 100 kiloparsecs. So this was to give you a sense of scale. This is what the density profile of our Milky Way looks like. Data points from our NGV survey. The dot line and the dot dash line come from 2 other competing surveys, the HITS survey, high latitude transient survey, and the dark energy surveys, of course, studying multiple, including stars and Mercury. I'm going to see this slide. Is it still part of this? No, very much part of the halo. Not at all. Density is still exponential. No, the density is a power law. It's log. It's not a log linear.
Can you clear where the disk stops?
So this case, and this not for these data, because we're looking perpendicular to the disk, we're looking towards the galactic pole here. So the disk generally goes out to something like 30 kiloparsecs. So this is well on that. In fact, the bump you see around 340 is Sagittarius. Sagittarius is everywhere, including in the foreground of the purple. So this is the work of PhD. Oh, let me see. Minus 3.5-ish. This one, I think. Let's see. Can we do this in our heads? The decade on x-axis, if you go from 8 to 300, and right. So I'm put my cursor at 30, and we're going from a few times 10 to the minus 1 to a few times to the minus 5. Times 10 to the minus 2 to a few times 10 to the minus 5. It's 3.5. What I mean. Okay. Now, talked about halos and why they're important for understanding accretion trees. If we look much at home, both in the Milky Way and in Andromeda.
To see whether the questions on this.
Yeah, sure. Any questions about our home galaxy, of this young man, or anything at all? Can't tell you everything about this young man. I can tell you things about him. Or should we do questions all together at the end? Whatever. Okay, since I don't see any hands before. So the other way to understand a galaxy's history is just to look at something that's relatively fragile within the galaxy. The disks of galaxies, the frisbee-shaped portions of galaxies are relatively fragile because it takes stars just move one plane to have a disk, and kind of lots of disturbances that can move stars out of a disk and change them into sort of a swarming configuration. For example, when 2 disk galaxies, massive disk galaxies collide, what you have with is an elliptic galaxy where there's no disk anymore, and the stars are all orbiting. They're all orbit, but no star cares about any other star when it comes to the direction of the orbit or the eccentricity of the orbit. So disks of galaxies are great thermometers for this whole phenomenon of dynamic heating, springs falling into a galaxy and causing it to put what's already there. I do want to share a little video with you, with no sound again. The universe doesn't make any sounds. So this is a video that my colleagues have put together a few years ago. What you see of this picture is the arc of the Milky Way, our own galaxy. It appears like a great circle in the sky. And Andromeda is this little crispy shaped galaxy right there. So let's see if we can zoom in. Let's see if this works. Not sure it is, so I may not. I may have to stop and play this movie different from. Sorry to do this. We want to play this movie, but I may have to restart mine. Where did it go? I don't deliberately did. I wanted to reconnect. That's fine. Buried deep in the crypto computer. Okay, so let me see if this works again. I was starting over there on Zoom. Coming up. Okay. Don't worry, I won't need to go through this whole slide just to show again. Let's see if this works. Doesn't. I'm going to just go to a standalone version of this video. This video is I'm holding you in suspense. It's a good video, I promise you. Okay, here we go. Let's see if this works. No, still not. So let me just play it alone and show for a moment. It's a spectacular video. So you have to see it. You might think this is all planned. It's all staged to build up the drama here. We go back a little here. This better work. Let's try this. Zoom seeing the correct video? Okay, thank you. If this fails, you'll have to come to my computer to see this video here. Okay, we're going to zoom in and this work. Okay, so you see the arc of the Milky Way, and you see the Andromeda Galaxy, but the Andromeda Galaxy is going to get a little closer as we zoom in. And we're going to zoom in more and more. You can see the galaxies. Those are breakfast and lunch for Andromeda coming soon. It's about to cannibalize those two galaxies. But as we zoom in, this is a simulation. This is an actual image of a section of Andromeda that was imaged with the Hubble telescope. So when Shomak and I created a mosaic of Andromeda with our students, we have 57 images from a mosaic in two filters. The blue filter and infrared, the BNI. This is a mosaic of about 3,000 images with the Hubble telescope. This is definitely the largest digital mosaic that the Hubble has ever made, and it was my favorite galaxy in the whole Andromeda. The individual dots in this picture are individual stars in Andromeda of different temperature. The stars that red are cooler than the star blue. I'm using cooler temperature symbol. You all are cool students, not that kind of cool. And the patches you see here, these dark patches that you see here, these are from dust in the Andromeda Galaxy. That's the plot of stars that are beyond. So I brought this up just to show you this movie and go back to my main slide set. How am I doing for time? Where should I wrap things up?
You know, after I mean,
Okay.
we started about 6:20.
Okay, I will do my best to.
If you can, like, but yeah. 20 minutes.
See if we can move this out a little bit. Okay, so I'm going to talk about the dynamical heating of the Andromeda Galaxy and the Triangular Galaxy. By the way, the Andromeda Galaxy is somewhat bigger than the Milky Way in size and mass. The Triangular Galaxy, by contrast, is somewhat smaller and lighter in mass than our Milky Way. And so we're going to study the dynamical heating of both disks. And this is what I'm showing you is from Claire Dorman's PhD thesis. Published this particular paper was published in 2015. Philip, you'll recognize this. This is the same paper that we use for our tutorial. So there's Andromeda looking very strange and all right, because it's taken in infrared light. So you're seeing not individual stars, but seeing the dust. Someone forgot to clean up the Andromeda Galaxy. There's a lot of dust, and the stars eat that dust. And dust glows in the infrared. This is a Herschel image, the European Space Agency Herschel image of Andromeda. But it's shown to the same scale, same part of Andromeda as the three others. And I'll explain the color in a moment. But the map that they put together for her PhD thesis is based on three kinds of stars. You can see old stars. Old stars meaning stars that live for billions of years, up to 10 billion old population or left. In the upper right, you see intermediate age stars that are around for a few billion years. And on the left, upper left is youth. Young stars, astronomically speaking, these are ones that live for much than a billion years, 100 million years, for sure. And the color coding is very, you can see the colors are very different in the face. You see mostly dark colors in the upper left. The colors get lighter when you go into intermediate age stars, and the colors get significantly lighter when you go to the lower left. What is this color telling us? What is this color? So we take every star and we draw a little circle around it on the sky and define its neighbors on the sky. Then we ask ourselves, what is the root mean square deviation of the velocities of stars within a circle? If it's high, we give that star a bright color, the star used to define the circle. We give it a bright color. If its neighbors that are moving have a wide range of velocities, we give it a dark color if its neighbors are all moving together. So it's the root mean square, not the mean velocity of the neighbor, the root mean square, the standard deviation of velocities. So stars, like a very well-trained marching band, are all moving in a circle. So if you look at a small piece of the field aerially, the people marching in a certain part of the field are moving at the same speed, same direction. So line of sight component of that doesn't have a large dispersion. By the time you get to old stars, they're not a well-trained marching band. They're like a marching after a heavy drinking. This is not something. This is something I'm not encouraging you students to experiment with, but something has kept these stars around during the time that they've been in the Andromeda Galaxy. So it's a measure of dynamical heating, and what they went on to do is, this is how stars are divided into different age groups. That's what's shown in this section of it. And what you can see is a very clear segregation. RGB are the oldest stars, one for the longest, have a much higher dispersion of velocity. Now, quantity dispersion is about 100 kilometers per second, typically, whereas the young stars are 20, 25. This is the dispersion in velocities of stars. And what you can see is a progression from the stars to the oldest stars. There's a y-axis is a measure of how coherent, actually a measure of incoherent the motion is. The higher the number on the y-axis, the more They said the bodies of stars are in the disk of the galaxy. Yeah, that is an estimate of how long the stars have been around as of the populations. You see this very clear trend. For our own galaxies in the Milky Way, the corresponding trend lines are shown in the orange and pink. For different components of the velocity. The comparison point is really pink to the Andromeda points. The orange points are more about the motion of radial migration rather than potential motion. You make different assumptions on the star formation history Andromeda. You get the old symbols instead of the fill symbols. But the basic point is Andromeda has had a more difficult view. It's had a more trough past than our Milky Way. Where Andromeda sits in the filament that forms the lobe may be what's responsible for this. But Andromeda has bombarded more. It's been more in the center of things when it comes to galactic cannibalism than our way. So this is something. It's a little bit of a dangerous conclusion to draw from this. Because the Andromeda measurements are global. They cover a large part of the disk, whereas the Milky Way measurements are relatively local to the sun's position within the fluid. So it's not as global a measure. Neither of them are pretty global. But the Andromeda measurements are somewhat more global than the given measurement. Yeah, sorry. Yeah, phi in the other. So in Andromeda, we're looking at line of sight. So it's really a combination of the two, because we are looking, whatever the projection is line of sight. We wanted to make this model free. So we are just looking at the line of sight component of Andromeda, which is some combination of the two. The combination of the three, actually. Even if you think about cylindrical course, then it's R and Z. Milky Way is R and phi only. This is R component and phi. Because for the Milky Way stars, 3D measurements. For Andromeda, we only have one component, the line of sight. Difference in slope, difference in height. Difference in height. Yeah, the slope really has to do with the rate of heating, and the height has to do with the heating. So. But it still maintains this. I know. So it maintains a disk that's about a kiloparsec thick. So there's a lot of debate in the Milky Way, not debate. There's a lot of description of Milky Way as having a thick disk. And whereas old stars don't have a thick disk. Bottom line, it has a thick disk. It's a kiloparsec thick. And so the young stars are in a thin disk, but not the old stars. That's a big thing to the way. Again, I'm always very nervous when I'm comparing my neighbor's house, my own, because I'm only viewing my own from my bedroom internal view. My walls are only translucent; they're not transparent. This is so. I want to be careful. It's always dangerous when you look at other galaxies and say it looks different from our own. Yes, of course, we have such a different perspective. What I'm reassured by is when you look at M33, it looks much more. It looks quite Milky Way. So we can see differences from the galaxy. I'll get to that in a minute. So there's Claire. She did a wonderful PhD thesis with me, and then started to use data science in the corporate sector. So she first was working for Pandora, the company, and now move people around by working for Lyft. A couple of my recent PhD students have gone into that. Okay, this is now a different aspect of Andromeda, and I want to, what happens is we start with a galaxy that is gravitational potential stars are moving around coherently in a circle. I take them around. Not only do their dispersion go up, but their net rotation speed goes down. So you get something called asymmetric, where the stars are not rotating as fast as the galaxy, so the speed of the hill. And that's what you see. This is from Amanda's paper, where it's quirk of 20. And I just want to put it. What is beautiful about this, in my eyes, is you see it in the data. So 4 age groups, main sequence stars, the youngest stars in the left, these panels, young asymptotic giant stars. These have an age of about 1 billion years. This is more like 3 to 4 billion year older AGDB, and these are sort of 5 and higher, or 4 and higher. And what you can see, every star in this upper panel is color coded its velocity. Every star, and every star, the dark color tells you the velocity of the star. Now, this may not be you, but Andromeda is certainly towards us. So all stars have negative velocities. The whole galaxy, someone once thrown a brick at us, the whole galaxy is coming towards us. It's going to cannibalize us for the story, and I'm not going to go into that. I'm not going to go into the Milky Way Andromeda collision right now. But what you can see is there's a very clear rotation pattern. The upper part of the galaxy is mostly yellow color. The lower part of the galaxy is mostly purple color. Now, mind you, the center of the galaxy is at plus sign. So we're really looking at the upper left half of the galaxy. We're not looking at the whole thing, but in the upper left part, the part that's close to the center has purple. This part has a color that's about 300. That's the speed at which the first speed translates towards us, 100 kilometers per second relative to the sun. So it's not surprising that if you look towards the center of the field, or along the minors of that ellipse, that you're seeing colors that are reflective of the translational speed of Andromeda. But over here, the reason it's yellow is because that part of the frisbee is rotating away from us as the frisbee moves towards us. That part of the rotation counters the rotational motion, so you get a less negative velocity in the upper left part here, minus 100 or so, or minus 50 even up here, compared to this part here. But what you see for young stars, good contrast between yellow and purple. What you see for the old stars is more like a red to purple. So the young stars are spinning rapidly and have more coherent rotation than the old stars that are spinning more slowly and have more coherent motion. So this asymmetric drift, as I mentioned, of age. Asymmetric drift on the y-axis, mean asymmetric drift as a function of stellar rate. This is again work from Amanda's thing and Amanda's PhD. Now this is looking at asymmetric drift as a version in the sky. Again, no spectacular trends here. And this is Amanda's work from a few years ago. Now, when we go to the triangulum galaxy, this is now smaller galaxy than either Andromeda or the Milky Way. What we see, what surprised us a little bit. Go to young stars in triangulum, to the upper panel here. What you see, sorry. Safe, yeah. Okay, when you look at young stars, the distribution of cities looks like a beautiful galaxy. Now, this is not the distribution of velocity. What's shown on the x-axis is the difference between the velocity of a star, line set and the velocity of gas, the hydrogen in the gas phase that's spinning. So it's in velocity, and you see that the stars follow the gas. The young stars follow the gas very well. The mean velocity, median difference in velocity between the stars and the gas equals to 0, and there's a narrow Gaussian on this upper here. If you look at older stars, just by contrast, that's the best fit Gaussian. The red line, the best fit Gaussian. Not a very good fit at all. It's under predict the central part of the histogram. It's over predicting for immediate at these velocities here. It's a much better fit if you make it a two-component Gaussian. If you take narrow and a broad component, it's much better. Sorry, the book is blocking you. In the lower right here is our two-component model of M33 kinematics. Two-component model. A component, dynamically component, where things are more incoherent, and cold component is coherent. Now, this was surprise to us. Trying this, the smaller the galaxies are, the simpler they tend to be. They tend to have single component. We have dwarf elliptical galaxies, everything is swarming. We have dwarf irregulars, where everything is disk. For triangle to have this multi-component structure came with surprise. No one had seen this dual component, and you can see it suffer. It took many stars survey to see this.
So what is that say up there?
Yeah, it must,
Not so small only.
yeah, but smaller than it. And strangely, this component seems to be confined to the center. So it could be one event, but it has something. It's done some that, and it's we're still trying to find out if it's, I don't know, but it's done something.
It would be surprised if they're eating more galaxies.
Yeah, it would be a huge surprise if they're eating more. It's a small galaxy, and it's got a very fragile disk. What does the kind of cannibalism look like? I want to show you sort of a forensic reconstruction of the so-called giant stellar stream in Andromeda. This is a cannibalism event in progress in Andromeda. This is the work of Ivana Escala. Oops, see in here. Sorry about the font change when I was going to talk from a different thing. Pick these shells up from a beach in Tel Aviv in Israel. And the reason I have a picture of shells here, because galaxies have shells in them. A spore system falls into a galaxy, gravitational potential. It goes past pericenter, and then at apocenter, it turns around, comes the materials back. You get a sharp edge there, and they're called shells. And I'll show you examples of shells in the Andromeda galaxy. This is a shell here. It's hard to tell, but until you edge filter this map, you see a sharp edge there. This is a filtered version of the map. So the authors wouldn't share their data with us, so we have actually filter their plot. All the labels show up. Sorry about that. But I want you to pay attention to these two edges here. This one. It's called the Western shell. And if student and you're confused, west is being plotted to the right, it's because in astronomy you're looking at a sphere from the inside. In geography, you're looking at a sphere from the outside, just to be consistent with latitudes and longitudes on Earth. West is the sphere here. So you can see that this is a shell. There's another shell over here for the northeast shell. This is the giant stream. Now, we had a model, computer model. Mark Bardo came up with this model, where a system thing, the green particles gone through pericenter once. Yeah. So they're trailing the mass of the galaxy. The galaxy's been spaghettified on its way in. So the center of mass, some objects are trailing the center of mass, some objects are leading the center of mass. So the green particles are trailing, they haven't moved one pericenter yet. The red particles have gone through one pericenter. The magenta particles have gone through 2, and the blue particles have gone through 3. And what you expect when you look at a shell in velocity space, at the edge of everything is much at turnaround, so not moving. So very low velocity dispersion. And the body of the shell, some material is moving out, some of it is moving back in. So you get sort of these triangular shaped shells in models of shells. And with a little bit of imagination, you can convince yourself that there is a triangular in that. Now, this has been the work of Ivana Escala. And what she shows is that you actually have not one, but embedded shells in this little plot. So you have red-shifted parts of shells, you have blue-shifted parts of shells, but the color coding is such that the points have an apex that's somewhere here. The pink points have an apex that's there. The points, you haven't got the apex yet. Yes.
Green has now gone to the very center.
Yes.
So how do they?
Oh, this is from model. It's from a model where everything is known. So we take a gravitational potential, we throw in a galaxy, and so since you know every particle's history and future in that relation, the particles, the coded things you saw were a beta simulation of a cannibalism event. So we're using that to predict what's going on in.
So here,
Observation. On this one, because see, in the parts of Andromeda, the 3 shells saw Again, three you saw were the magenta. The red is the first one, single pericentric path. Magenta is the second one. Two pericentric stages, and blue is the third pericentric passage. All three, you get a triangular shape. So blue, pink, and red. And what you're seeing is dynamical friction in the galaxy, with each pericentric passage is not going up each time. The apex of the triangle is getting closer and closer to getting smaller and smaller. So the blue point, apex that's up here, the big points have an apex somewhere here, and then the red points, the apex will be on this. So an example of dynamic friction in action. You can see the red points shown in both panels.
I think doing those problems from one side. In the previous slide, green in the bottom.
Yeah. That's where the cannibalized is falling in from that side. With respect to the center of the galaxy, 0, 0 here is the center of Andromeda. And these coordinates, 8 interns, are sky coordinates relative to Andromeda.
How do you make that? That particle has some boundary. So,
which boundary do you see?
boundary is from where this velocity degree. Right part of the.
Oh, on this one. Yeah. Oh, bottom part here. So this is the bottom part is a simulation. The upper part is the object. So the bottom part, no, it's because you know everything about a simulation. You created it. You can play God. You know where the particles are still around and all that. So the bottom part is a simulation compared to observations, and the blue points in relation have an apex that's very similar to the app state. So to suggest that even this northeast, which is the hardest to detect, three pericentric passages, even that can be detected in the data. Not every star in our survey is from the east shelf, right? There's superposition. There's stars that are in the foreground of Andromeda. There's some that are part of that shelf. That's why you're not just seeing a triangle there. You're seeing a triangle superposed on other stars.
And
This one, this is where that's falling in for the first time. This is material that's falling in.
how do that one?
So what happens? This is very velocity gets closer and closer as you get further away from it. It's falling in for the first time. As it approaches the center of mass, the velocities get more and more negative. That's how you get this line. Simple trend line. Right? If you drop something, a series of things into a potential well, things very far away are going to have a velocity to zero, and things are approaching the potential of the most velocity from our perspective. It's falling in from the far side. That's why negative velocities from the far side.
In observation, you are taking all of this. That's why that age is.
Exactly. We don't see that edge so clearly because we're looking at the center part of the galaxy. We're not actually following the shell. We have written paper where we follow the shell. You see something very similar to green.
Oh.
I will do that. Okay. So this is what we're doing at the telescope. Now we are targeting the lower part. That's where M32 is. And this is the work that we're, this is M32 with some Hubble pointings around it. And our goal is to measure the 3D motion of M32 against M31. And I'm just going to you. There's a single pointing with the full advanced camera survey, ACS. That's that purple quadrilateral. In that, we're measuring the position stars as a function of time, and the shapes are from spectroscopy with the telescope. And I quickly show you a histogram like this. Histogram of velocities relative to the sun heliocentric velocity, and you see two peaks. One of those peaks is associated with Andromeda. Those peaks is associated with the M32 galaxy. So this is the M31, this is M32. And if you march in closer to M32, you can see the contrast. the peak on the right becomes much stronger if you restrict your to stars that are close black blob there. And if you were further away, then it's exactly opposite. The peak on the right of the dotted line, this is the dotted line, by the way, is the mean velocity of Andromeda towards us minus. And so we have much more data now, and we understand what's happening with M32, the galaxy. So we are using the magnitude information. This is the work that Mark Fardo, Research Space Telescope, is involved in. Okay, I'm going to skip these and take you to away from all this. I'm going to spend a minute on this and then go to our summary. One of the things we're starting to do is study galaxies that are further away from Andromeda. And they're so far away, individual stars are named. So we're using a technique that postdoc and I invented a few years ago, where we are helping, we are asking nature to help us. We look at SPF, self-brightness fluctuation. If you look at a map of a galaxy, no two pixels can contain the same number of stars. Right? As you take the galaxy further and further away, the brightness per pixel doesn't change. And as you take it further away, the more area, physical area, or per pixel, so there means there are more stars, goes like this distance squared to take the galaxy away. But there are, each star, brightness goes down over d squared as you go further and further away. Those two effects exactly can cancel out. So the mean surface brightness of a galaxy doesn't change. Brightness per unit day doesn't change as you get further and further away. What does change? The amount of fluctuation from pixel to pixel. So the closer you are, the fewer stars there are per pixel, and the brighter those stars are. So you see sun fluctuate the closer. So this self-brightness fluctuation, something been well known, and Tonry and Schneider just use this to measure galaxies. What we're doing here is we're saying, let's take each of a galaxy where we count individual stars. But when we see a pixel that's bright, that means nature has co-added stars for us. Let's put our slits on those pixels. Because the galaxy is too far away for us to measure the spectrum of individual stars. So we put slits where we combinations of more than average, the higher than average number of stars in those pixels. We do that, and just to give you an example, on the left, showing you surface brightness fluctuation, which is pixel variation. If you take a Hubble image, you can see, because there are, there's a concentration of stars here, concentration is here. It's not a single star that's causing that brightness fluctuation. So we take areas of the galaxy that these zoom-ins are from this part where we Hubble imaging, but we're interested in this little sphere. This is a small galaxy eating an even small galaxy. This is a galaxy that's 3.5 megaparsecs away, and eating an even smaller galaxy. You can see that the smaller galaxy has been stretched out, and we measured this through the thread. We were able to measure the spectrum of co-added surface brightness fluctuation. And this is a different system where we can see the galaxy is being stretched out. This is in the Pisces survey, being stretched out, and actually see a velocity gradient along this. So if we take spectra, and we can see a velocity gradient from one end of the stream to the other. So you can see streaming motion because of the orbit of this material. So here's an example of the cannibalism in act. This is the then postdoc Elizabeth and Dinius and Rich. They're both faculty members now. It's the work we've been doing. Okay, so I'm going to skip rare populations and go straight to our summary. Okay, so said a little bit about the accretion history, chemical enrichment, and extent of the Milky Way stellar halo through the halo 7D and days. Something about the Andromeda galaxy's stellar dynamics and satellite interactions. Something about the triangular galaxy, triangulum is called in 33, through Splash, Patter, and the T-Rex survey. Part of triangular studying, we don't call it Splash anymore, we call it T-Rex. you a little bit about covalent. I didn't get a chance to talk about these chemical anomalies or about variable stars in M31 and M33. Let me stop here. Thank you very much for your attention. And happy to take questions.
Thank you. Thank you, Professor GuhaThakurta, for the nice talk. So now I'll be looking at the topic.
Oh, yeah, there is that. I'll leave my slides on in case you come back to one of those to answer your question. All right, very good.
Good evening, Professor. My name is Roshan. Brilliant talk, and I had this simple talk question. With my very limited physics, I don't seem to understand why really big stars like greater than AGB stars, young big stars are very stable in their motion and quick in their evolution, in spite of being very violent internally. While mainstream like balanced stars are
No, that's a great question. Let me. I'll do my best to answer. So, these really massive stars are huge gas clusters, in automobile terms. So they use up their fuel very quickly. So when we see them in Andromeda, it means they were formed a short while back from gas, from hydrogen. That is forced to be well ordered because gas clouds have friction. They're forced to be well ordered. And material is formed from gas clouds. The stars formed from a disk of gas. They tend to be well ordered because the parent material is well ordered. So our thing, these massive stars have beautifully coherent motion, well-trained moving band, because they haven't had much time to get kicked around. They don't live long enough to get kicked around. You might think that they're lucky, they don't get kicked around, but guess what? They die very, very quickly. So they're not lucky at all. It's the others, the low mass stars, live for 10 million years. Because we see, on average, some would have formed recently, some would have formed 10 million years ago. On average, they're 5 billion years old. So it's a long time kicked around by cannibalism event, by giant molecular, the gravity of it goes by the bar at the center of Andromeda, not the kind of bar by alcohol, but there's an elongated structure at the center of Andromeda that acts second an egg beater. So there are many sources of them. Next task is to figure out which of these is most important.
That slide about the similar stars falling in. The green ones are falling in the first time.
That's right.
Wouldn't you expect tracer and gas?
You might expect them. So, sorry. You think this galaxy that fell in got stripped of its hydrogen before it got tidally emitted? There's, one of the things we see in the galaxy. It comes from a different set of about it. Did not present today. When you look at the age of stars associated with that giant stream, they tend to be 4 billion years old and older. Maybe 3 to 4 billion years old and older. The time scale of its destruction is less than a billion years. We know the time scale very well. You measure velocity, measure distance, you divide by the other. So we know how far away those stars are at the tip of the far tip of the stream, 100 kiloparsecs from the center of Andromeda. We know how fast they're moving relative to Andromeda. A little bit of modeling, we're measuring one component of the velocity. And the number you get is 0.7 gigayears. So why did the thing that started getting disrupted 0.7 gigayears ago, what stopped forming stars 4 billion years ago? We think it's because it got rid of its gas. It fell the hot halo of Andromeda. Andromeda has a hot plasma around it, strips the fuel from our galaxies that are falling in. And we can see this in the Milky Way and Andromeda, almost close satellites stop forming stars around the world. Because even while the galaxy is still intact, before it gets gravitationally disrupted, it gets RAM pressure stripped of its fuel.
That would you do see galaxies in other galaxies.
You do. They may have weaker plasma. They have
You're
halos.
saying that with galaxies also for large galaxies.
That's right. And in fact, in Andromeda Milky Way, the only two galaxies have gas in them are the CNS. Nothing else does. Everything else has been stripped of us. So we think the LMC and SMC sort of have temporarily at least escaped being stripped. Everything else. Besides Sagittarius, all the sides of Andromeda.
The strangulation before that.
Right. Very good. Yeah. Strangulation for camels.
This star being 300 kilophotos away. Which are then by from the dark matter. Are these associated with the galaxy, or are they coming from various blocks?
Yes to both.
Where are they?
No, yes to both. I mean, these are the remnants of cannibalism in the Milky Way. We've now to measure velocities of these things. They are co-moving with the galaxy. They are not. They have nothing to do with the Virgo cluster, which has velocity of 1,000 kilometers per second on range. These are very much the foreground. They have average. They have a velocity of 0. One of the beautiful things about these galaxies, they're towards the galactic pole. They're away from the LMC. The reason we went velocities of these because the LMC should be some damage to our galaxy. Should be pulling on our disk harder than the distant stars. So we have to see a velocity gradient with radius. We haven't seen that yet, but sort of the type of the LMC is what we're hoping to see. I haven't seen it yet, but that's why we're measuring velocity. What we're also finding out is in these other competing surveys, the things that we call RLR are turning out to be background quasars. So we have to be really careful about this. We haven't found any background quasars yet in our survey. We're finding them in others. Things that are stochastic variants, not particle, that are being misclassified as RLR at large distances. So we are working very hard to clean that up in our own survey before we publish. Yes.
Question in interaction. You mentioned that it's two places or velocity dispersion. The larger velocity dispersion is to the center.
That's right. Yeah, it doesn't look like a halo.
So I was wondering what you interpret that as a merger. Could it not be just local gravitational?
It could be. It could be.
Yeah.
We don't think the central black hole is massive enough to be doing this because it still has a size of that's about a third of the disk. So it's not completely central. In fact, we've been referring to something as the femur bone of the dinosaur. When our stars, when they first made a map, didn't look like a dinosaur. It didn't look like a T-Rex. Actually, it looked like a Parasaurus, which is a particular type of dinosaur. In the bone of that, there's a young stars that are high dispersion. We don't understand. So there's something local going on in the central part. See, Parasaurolophus is a very hard acronym to build into your survey. But I wasn't going to be defeated. So what happened was Parasaurolophus take that word and the word surface, which I really wanted to name survey. I couldn't find an acronym. I was defeated. So I took those letters and I made an anagram with those letters. And we slipped that in paper by acknowledging double A sulfur overspray. And then the referee, it got past the referee and editor. They didn't ask us what this project was. But it's really you can look up the Keck and Hubble 2022 that actually has this in the knowledge. It's the only time to prank like this. But I feel I owe it to myself over these years. Okay. Other questions? We have time.
Yeah.
We're looking at density and starting at such high speed. Are there any indication effects that
You know that the velocities we're talking about are very small compared to the speed of light. The overall speed 10 to 100 kilometers per second. Speed of light is 300,000. Certainly our velocity measurement methods are not sensitive enough to detect any gravity, any general relativistic effects. No, sorry. sorry to disappoint you. There are GR costs seen around the stars that are moving around the center of our galactic black hole. This is and that's what's been the developed. Let me see if I can pull something here really quickly while questions begin. Let me. Any other questions? Okay, please go ahead.
Professor, when stars get stranded while two big galaxies are what determines the speed and velocities of these stars, these rogue stars that are?
Well, that's a very good question. A very good question. Let me see if I explain this. When two galaxies collide, sorry, this is coming up here. When two galaxies collide, when two galaxies come together, they're in orbit around them. Why do they merge? Because energy is conserved, they just continue orbiting the wind. There's something called dynamical friction of the great undertaker, but galaxies actually, the system loses their energy by sending some stars off big from the system. Those stars carry energy from this, and they are of course the more energetic stars are the ones that lost, and that leaves system with less energy. They get closer together. This process continues until the galaxy. This is not Caroline's paper. Let me go back. This is Caroline's paper. It's not Amanda's paper. What I want is the other paper that this one is this one. Yeah, does that make sense? So stars, so galaxy collision like corporate murder. Some people get laid off, but they actually make the company healthy. They make their what's remaining healthier because they take away energy in this case, and what's left are more negatively. And galaxies get closer together, and the process sort of runs over to galaxies merge. I'm looking for the acknowledgement section so I can highlight my AA sulfurous overspray. And on this AA, think of a AA out in the sun. You're going to get a sulfurous overspray when the batteries explode. That we did not. There is acknowledgement. Who needs it? So, self-AA overspray. Sorry. You can see that it'll spread. It'll spell Parasaurolophus locus survey if you. The pity is that I'm not making this up. We did get past the referee months. The editor would catch. This is a good test. You should do this all the time, but it'll test us whether you're a referee away or on your editor.
You should do it during talks to check whether people
Other questions?
There was one we were saying.
Well, a few years ago, if you'd asked me that question, I would point to the White House first, but no, sorry, I don't have an internal answer to that question.
If not, then before saying this, I would like to call the concert. We have the for
No, but thank you. That's first to many visits.
Yes.
Thank you.
thank you.
Stick around for a few more minutes. I don't know if you want me to stick around here if people have questions. If they're there, you can ask questions in front of others here.
You can stop your YouTube.
Okay. Should I stop the recording here?
Yeah, I think it's proper.
Oh, you stop the recording, right?
Oh, she's,
Okay, that's good.